Hello and a warm welcome to our month-long celebration of the Science Festival, which will culminate into the Mars orbital mission. Over the past few weeks, we've been showing you various programs related to science exploration and research and its applications which concern you and me in day-to-day life. Today we are at the esteemed Tata Institute of Fundamental Research in Mumbai, which has played a pioneering role as far as the basic science research in the country is concerned. But when you talk about the basic science research, neutrino particle is one particle which has evoked a lot of interest amongst the scientists and the physicists across the world. But what exactly is this neutrino? Joining me now is an esteemed panel of guests. To my left is Professor Amol Dighe, who's from the Tata Institute of Fundamental Research, Mumbai. We have Professor Nabha K. Mandal, from TIFR. Then we have Professor D. Indumati, who is from the Institute of Mathematical Sciences, Chennai. Professor Vivek Datar, who is from Bhabha Atomic Research Center, Mumbai. And Professor Mohammad Naimuddin from Physics Department, University of Delhi. Welcome all of you on this special show on Rajya Sabha Television. I would like to begin with you, Professor Mandal. I remember when we were in grade 4 and when we were studying about atom, it consisted of electrons, protons and neutrons. But when you talk about neutrino, is it something which is an extension of all these three particles which we have studied?
Well, I mean, it is to some extent an extension, but what you have learned about proton, neutron and electron when you are in your science class, and the proton, out of that, proton and neutron are really not fundamental particle in the sense electron is.
Okay.
So now we call quarks. We have up and down quarks and electron. And the neutrino is one such elementary particle.
Okay.
And actually it is just like an electron, but only thing is it doesn't have a charge. Okay. So there is the difference.
But it is the latest fulcrum of excitement for the physicists and the scientists across the world. Why so?
Well, it has to be because it is one of the most abundant particles in the universe.
Okay.
So, sun, for example, gives out lots of neutrinos, a trillion of them.
So, when you say abundant particle, we also have photons which are in abundance. So, how would you really differentiate them?
So, there are about half the number of neutrinos in the world as there are photons.
Okay. Okay.
If you look at the sun, which is what we see every day,
right,
about 100 trillion neutrinos from the sun pass through each of us every second. Okay. So, these are so abundant.
But so from what you're saying, I gather to understand that the scientists know what neutrino now is, what it is capable of, but probably you don't have the technology to detect what it can really do to future?
That's true. So we know about neutrinos, we know some of its properties, we still don't know some. For example, we don't know what its mass is. Okay. But from whatever properties that we know, we can actually infer about where they come from, the stars, for example, sun, what they do in the sun.
Okay.
But still there are lots of things that we don't know about this.
Right.
And once we learn more about it, then we can think about what use to put it to more and more.
Okay. Professor Indumati, if I could come to you. Neutrino, what is the need for building an underground lab for neutrino when you particularly talk about that?
So this has to do with actually not the neutrino itself, but what other particles we receive on Earth.
Okay.
Earth has an atmosphere which blocks a lot of particles coming on the Earth, but this atmosphere is also responsible for creating also more particles on the surface of the Earth. And if you just look at the number of cosmic rays, in fact the origin of these cosmic rays is still an open question in particle physics today, but if you look at the number of cosmic rays reaching us, and many of these are charged particles like protons and a kind of a partner or cousin of electron called the muon. So all these particles will just bombard the surface of the Earth.
Okay.
But being charged, we know that the Earth is like Earth is like electrical neutral, right?
Okay.
So once these particles go through the Earth, they get absorbed over some distances.
Are you saying that when the cosmic rays fall and the other particles are also traveling, so it's only the neutrinos which go underground and the other particles get filtered?
You have
something like that?
Understood it. So in fact the Earth acts as a filter for these other particles. So because neutrinos are very weakly interacting, in fact Professor Nabha Mandal already said they have no charge.
Right.
So they cannot interact through their electric charges because they have none, right? So they interact through a force which is called a weak force, and the name itself tells you that this force is very weak. So they are very weakly interacting, which is why all those trillions of neutrinos that Professor Dighe told you about coming from the sun go through you and don't do anything to you at all.
Professor Datar, it's something very interesting. It's a weak particle, but at the same time it's called a ghostly particle. You say it's a mysterious particle, not much is known about it. What is exactly, I mean, what lies at the core of this particle? Why do people really call it it's a ghostly particle?
Ghostly
And
comes
there's
about
lot
just
of
because
apprehensions which have been spread. especially in India, you know, when it comes to the development
ghostly
of
just comes about because it's hard to detect. So it
Okay.
passes through you
Right.
and you don't know that it has passed through you. That's the ghostly aspect of it. But the interest is of course because it is one of the least understood particles. It can probe, as you say, things which we do not know things about. For instance, we did not know directly about 50 years ago that nuclear reactions were powering the sun.
Okay.
And it was through neutrinos that we came to definitively understand what is going on at the core of the sun.
Right.
So just as you have an image of the sun, which you can photograph, you can see, similarly we have now an image of the sun in the neutrino spectrum. Okay, that's a beautiful thing that has happened.
The only thing it takes long time.
Yeah, it takes a long time to make such a picture, but
Okay.
it can be done. I mean, it has also
It has been
poorer
done.
angular resolution than optical resolutions and so on. But still, at the level of technology, we at least can make an image of the sun in neutrinos.
Professor
Okay.
Naimuddin, if I could come to you. Now, one question which comes to my mind as a layman would be that what can be the applications of neutrino, the immediate applications what you just spoke to, what you were talking about a short while from now?
Well, neutrinos directly, immediate application of neutrinos may not be the direct application as of the moment, but what you do when you do any basic science, for example in case of neutrino, you have to detect these neutrinos. So in order to detect these neutrinos, as many of our guests has already told you, that it's a really weakly interacting particle. So you have to develop good detector technologies so that you can detect this mysterious particle which is
Okay.
least interacting. And in order, the detectors that you develop for detecting these particles has immediate societal applications.
Right. But if I could just button, Professor Datar, when Professor Naimuddin is talking about the detectors, I'm told that we are having a special ion calorimeter which is going to be placed inside that observatory which is coming up underground in Madurai. What is so special about that detector really?
Okay, this detector consists of a huge amount of iron which is
Okay.
magnetized, and this iron is interspersed with so-called active detectors. They are gas detectors which tell you the position of the charged particle that goes through this detector.
Okay.
These charged particles are produced as a result of interactions of these ghostly particles
Okay.
with the iron. So
Okay.
the iron has two purposes. One is to provide for target nuclei with which it can interact,
Right.
and then produce secondary particles which can be detected by these gas detectors, and also to provide a magnetic field. Iron is easy to magnetize.
Right.
So ICAL will be actually, when built, the biggest electromagnet in the world.
Okay.
Okay, it will be a 50,000 ton magnet consisting of 3 modules, of course,
Right.
each of about 16, 17 kilotons. And so these muons which will be produced when the muon type of neutrinos interact,
Right.
which is what we are going to mainly measure, they will actually bend, and the bending will depend on the charge,
Okay.
because you can have either mu plus or mu minus, positively or negatively charged
Right.
muons produced as a result of neutrinos or anti-neutrinos interacting,
Okay.
and then they can be tracked.
So once this process is done, you can see the actual mapping happening somewhere, no?
Yeah, you will have visual displays
Right.
of these muons bending
Okay.
and so on. yes.
Okay, the entire path
in
you mean
X
to
and
say
Y
can be
planes,
displayed
yes.
somewhere.
Right.
In fact, I was coming to you, Professor Mandal, on this INO project. There have been a lot of reported delays, protests, there were a lot of challenges in coming up with this entire INO project. Just take us through some of the challenges which you had to undergo. I mean, your TIF, or rather your truck with the government, the bureaucratic processes, the kind of delays you had to face as far as the environmental protests and all are concerned?
So I'll put it this in a different way. We had actually crossed many hurdles.
Okay.
So for example, I mean, when we are looking for a INO site, and then we of course we need a site underground, so whom do you go? You go to the Geological Survey of India. So
Right.
they actually shortlisted some site for us, and for example, the current site is one of them. Now, when you go and see that site, then immediately the local population or villagers, they will get suspicious. I mean, what are these people are coming at their backyard and talking some weird language like neutrinos and all those things they want to detect? Obviously, they will be suspicious and for us one. And then on top of that, when you do that, there are people also, they are not from the local. They are coming from outside again, and they are telling all, immediately we start talking about neutrino experiment, they will start talking all the bad things neutrinos can do to the human being.
I remember having read it somewhere, if I'm not wrong, you might correct me, Dr. Indumati. I was reading it that probably it's a source of some kind of a nuclear bomb, or
Yeah. All kinds of
all
things
those kind of
have been
myths were being
said,
spread about it.
Definitely, yeah.
So actually, so we actually took a sustained outreach program. We talked to small groups of people, large groups of people, local people. Then what we did, we went to the local colleges and universities and talked to the students there. And the students, they quickly can understand that what we are doing, what is the excitement about.
Professor Mandal, when you embark on these kind of outreach programs, I'm sure it's not a very easy task because you got to convince the local people, the students who are interacting. How difficult really is it? Especially when you're talking about a particle about which no one knows anything.
So it is. I would say that it is a complex thing that we have to do it sustained way. But once you start seeing the result, and it is really rewarding. For example, when you went to talk to the students first, and they got excited actually, some of them got excited, and it is actually easy because then students are talking to their parents who are the basically local people, and they get convinced about the importance of this science. And finally, what happens in 2010, the local collector, the Teni collector, he organized a meeting, and that was attended by something like 2,000 people and local people, and we have to explain them every part, answered all the questions, and after
that was a kind of a victory rally for Neutrino at that point of time.
Of course, almost like that. At the end of that rally, the collector announced that the local people are now convinced about the usefulness of the project to be here, and we were there. So it is a sustained project. I mean,
but what stage is the observatory right now at Madurai?
So this observatory is right now that government. So our project is funded by the two departments of science in this country, that is the Department of Atomic Energy and Department of Science and Technology. So, but the main actually the piloting department is Department of Atomic Energy. So our project, we have been given the proposal with all the funding required, and it has to first approved by the Planning Commission, and then it has gone to the what you call the Atomic Energy Commission. It is the complete project. In addition, because it is because the Department of Atomic Energy and Department of Science and Technology is very serious about the project, they have given us what we call the pre-project funding of the order of something like 86 crores of rupees to start the preliminary work there. For
but when you talk about the pre-project preparation, it's like building the tunnel, placing the detectors,
not building the tunnel.
All that.
So all the R&D, complete the R&D of the detectors, define what will be the parameters of your detectors, and then do some local development work in that place, in the sense of fencing the area and making roads, bringing the water, because we have even promised the local people that we are not going to use your groundwater. So we are bringing water from a river which is 15 kilometers away through pipeline. All these works we are doing in this pre-project fund.
But Professor DK, if I could ask you, projects like these, when they come up, especially in natural habitats like the one which is just coming up in the Theni district of Tamil Nadu, this INO project, how can it really help the local people over there? Because a lot of tribal population, a lot of local people who are staying and who would be staying around the observatory, how will this project really help them?
You have to look at two different things actually, the schools in that place, the colleges around it, and the local population, because the local population is not related either to the schools or the colleges, right? So when you go there and ask their questions, they are not questions that you or I would think of. I mean, their questions are, can I still graze my goat in your land? Okay. So no, we had a lot of learning to do actually. In fact, many of us who have been going there over the years.
No, so which means that they're still concerned about their livelihood.
Yes. So I think.
But will the project really cater to their livelihood?
No. So that's what I said. So what I'm saying is we had to even find a meeting point first to understand each other. Okay. So their questions were, we needed a culvert here, we needed a street light there. So it's at a very different level. But one thing I think now they have all appreciated, we said that look, as a basic sciences project, many of your children who are going to college can actually come and do a summer project with us. And that they can understand.
So that's a ray of hope you've held out for the local people.
The other aspect of any big science project is that you invest a lot of money which has to be invested locally. Because building the tunnel and all these kind of things, so it also brings employment for the local people. That's one of the spin-offs you can say, because then there are a lot of tenders that only locals can do.
So of course, it's a very big challenge convincing the local people of whichever science project is coming up. I'll have to take a short break here, but when we come back, we talk about other neutrino projects which are existing across the world. Back in a moment. Welcome back. You're watching our special program from the Tata Institute of Fundamental Research, Mumbai. Professor Mandal, if I could start with you. There are various other neutrino projects in countries like Italy, Japan, which have made some kind of a forward movement. So is there going to be some kind of a link with the project which India is going to come up and the ones which are really existing across the world?
Yeah, surely. So what is happening now, the neutrino is one of the most exciting area of research in particle physics today. As you have learned from other panelists today, that we have learned new exciting things about neutrinos. That neutrinos have mass, they oscillate from one species to another, things like that. So in this process, we have to learn many of their properties completely. So for doing that one, there are many experiments are also being planned or already operational in elsewhere of the India. For example, there is an experiment going on in South Pole, in below 1.5 kilometer of ice at the South Pole, which is called ice cube.
Okay.
This detector is a kilometer cube detector in the
Okay.
ice.
Okay.
And this detector is looking for neutrinos coming from astrophysical sources,
So
very
what,
high energy
so what you
neutrinos.
mean to say that this one particular detector has been placed inside the ice cube,
Yes.
one could be under the
So,
sea
no,
and one could
yeah,
be underground,
there-
like
there-
what the
yeah.
one is coming
So
up in
this,
India.
this experiment is addressing the issue that what are the sources of cosmic rays, what are the
Okay.
sources of neutrinos.
Okay.
There are two experiments and actually three in France, in China, in South Korea. These are looking for neutrinos coming from the nuclear reactors.
Okay.
Using that, they are studying some properties connected to the neutrino oscillation.
Right.
It's called the mixing angle.
Okay.
So they are determining that one. Now, one of the key question that we still have to answer in the neutrino physics is that we know that neutrinos have masses, and we know there are 3 neutrinos, right? And but we do not know which of these 3 neutrinos is the heaviest, which one is the lightest.
Okay.
Okay. So this question is called neutrino mass hierarchy.
Neutrino mass hierarchy. But Professor Datar, if I could bring in you, what Professor Mandal is talking about, are you really hopeful? Of course, there's a word called leap of faith, which is very big in science. But with this INO project, which is coming up in India, are you really hopeful that you will be able to cater to all these kind of requirements which you're actually looking at?
Yeah, I mean the detector that is being that will be built will hope to measure this mass ordering
Okay.
of these three species which are analogous.
But why is it there is a confusing signal when you talk about the mass of neutrinos? Some say it's a zero mass thing. Some say no, it has a little mass,
Well,
which is measured in terms of EVs, or I'm not too
No.
very clear, but
Okay.
in some kind of units it's measured.
So we know certainly that at least 2 masses are non-zero.
Okay.
Whether or not the third is zero, we don't yet know.
Okay. So that has to be detected.
That has to be found out.
Okay.
But right now the question that is important is whether, as he said, how are these 3 masses ordered? We know the ordering of 2 of them.
Okay.
We don't know whether the third one is higher than these 2 or
Okay.
lower than these 2, because
Okay.
that difference is larger.
Okay.
So we don't know whether it's up here or down there.
Okay.
Now that question is important because if you want to address another important question, which is even probably more fundamental, is that why is there a preponderance of matter over antimatter in the
Right.
universe at
Right.
large?
Right.
That question, if it has to be answered, we have to know an answer to this question as well,
Okay.
at least in many of the experiments.
So,
Now-
what you mean to say, does it have any relation with the Big Bang theory? Professor Naimuddin, if I could bring in you.
Yeah, so we know that from the Big Bang theory that the current matter that we see around us in the universe, it's only about the 4%,
Okay.
and about 15 or 16% of that is the dark energy. So about 80% of the matter is missing,
Okay.
and we say that's a dark matter.
Once this distinction is complete between matter and antimatter, what is the immediate application where you could actually apply this in terms of technology? Because that is one question which comes to every mind, and that is that where can you use that technology immediately?
See, technology usually follows fundamental science results after some time, maybe decades or maybe even centuries.
Right.
So right now, as you said, our main emphasis is to actually understand things and then see where they take us.
Okay.
Or as Naeem said some time back, that the technologies that come off as the spin-off for what you want to do.
Right.
Okay. However, I may like to say that there are certain kind of technologies that we do expect to develop in the next few decades, which will be very important
But when you talk
for
about the
us.
spin-offs, what are the kind of spin-offs you're talking about, the technological spin-offs?
The kind of spin-offs that already have come are, for example, in medical imaging
Okay.
kind of techniques,
Right.
or Cherenkov
Even the accelerators that we use
Right.
for treating cancer, for example,
Right. Right.
it's a spin-off from basic science.
Okay.
So people who made the accelerator first, they were not making the accelerator for some application. They were trying to understand if they can accelerate particles or not. and that's how the accelerators came into existence. And now you can see the uses. Almost every hospital
Right.
has an accelerator.
Right.
So that's like a spin-off of basic research.
Can I put it a different way? I mean,
Yeah,
I think
yeah,
the
please.
basic research comes first in the
Right.
sense 100 years ago when the electron was discovered, you didn't know to what use you could put it, right? You didn't have, I mean, all our conversation is being recorded through electronic equipment which needs these electrons to move, and
Right.
you need to understand their properties before you can apply them in any technology. So I think that first we should understand that this is a basic sciences project. So we're still trying to understand the nature of this particle. And I think the best analogy is the blind man with the elephant, right? So all of us have seen different parts of the neutrino. You know, we have seen, you know, somebody's felt the trunk, somebody's felt the tail, somebody's felt the ears, and we don't know what kind of beast this is.
Right.
So the question about applications and
It's a very-
technology.
That's an excellent analogy which has been given to you, given by you. But Professor Dike, if I could ask you, when you talk about projects like these, you know, like J.J. Thomson, when he came up with the discovery of electron, and when the Queen of England asked him, he said, well, "Who knows? You might just tax it one day." So when it comes to the economics of neutrino, are you really hopeful that in terms of generation of money or maybe making faster buck, in terms of those things, neutrino could be helpful in any way?
Well, let me first tell you about the use of neutrino that we know we could put it to, maybe
Okay.
not now, but in a few decades,
Okay.
and which is, for example, for nuclear non-proliferation.
Okay.
See, the property of neutrino that we just heard about is that it's very weakly interacting,
Okay.
so it passes through everything,
Okay.
which means that it's impossible to hide neutrinos.
Okay.
If we are able to now develop technology to detect neutrinos efficiently, it means that after a few decades or so, no country in the world, absolutely no country will be able to make a clandestine nuclear reactor or
Okay,
a nuclear
that's very
weapon,
interesting.
because wherever you make it, you can't hide it, somewhere else you will detect it.
If you
Right.
permit, there is another application, for instance, that this neutrino could be put to, and that is to do prospecting of uranium and thorium. In fact, about maybe 15 years ago, there was a paper by one of our ex-colleagues, Professor Raghavan, and that said that, you know, if you had a few 10,000 ton detectors, a few places in the world, you could tell what is the uranium thorium distribution
Okay.
in the globe. That just cannot be done any other way.
Okay. No, but is it true that where
This is
you
exactly
develop-
using the same property that
Right.
neutrinos can
So-
penetrate anything.
So which means the nuclear reactors also would be a source
They are
for
a
neutrinos?
major
Oh,
source,
yeah.
yes.
That's what I said.
They are
what
very
Professor
useful
Baba
actually
Badan
sources.
talked
One of the
about.
key parameters has been discovered that way, has been found to be non-zero.
Okay.
In fact, the neutrinos were first discovered using neutrinos from a nuclear reactor
Okay.
in 1956.
Okay. Okay.
And in fact, this what Naeem was talking about, particles and antiparticles, right? Actually, the sun emits neutrinos,
Right.
and reactors produce anti-neutrinos. And it was during this process of discovery that, you know, they actually realized, because what do you mean by an antiparticle of a chargeless object, right?
Right.
I mean, he said proton plus antiproton is minus, but neutrino has zero charge. There's,
Right.
you know, plus zero or minus zero are the
Yeah.
same. So to understand really already what it means to have an anti-neutrino was very difficult, and it actually came through understanding that
Right.
the particle emitted in the sun and the particle produced in the reactors are two different things.
Right. But another very big source of neutrinos are the supernovas, which everyone is talking about. How much of research has actually gone forward?
You have asked the right person,
Okay.
as an expert in supernova neutrinos, Professor
Okay,
Dike.
so I'll ask Professor Dike on this. So, how much of the forward movement has happened when you talk about the supernovas as becoming the most important source of neutrinos?
See, mankind has been observing supernovae for thousands of years. We have
Okay.
records from the 10th century and so on. Okay.
Okay.
However, neutrinos from the supernova
And supernovas, if you have to bring it to the language of the common man, is nothing but the explosion of the big stars.
for
no?
big star, yeah.
Okay.
The big star explodes. In fact, it explodes because neutrinos push it from inside.
Okay, okay, that's
and so they
interesting.
play a large role in exploding that.
Right.
Maybe before going there, I'll take you a small thing about supernovas.
Huh.
All the iron that we see on the Earth
Okay.
has actually come from the explosion of some supernova which happened somewhere.
Okay,
Okay. So
okay.
all hemoglobin that we have that
Right.
we use to actually absorb oxygen
Right.
has come from the explosion of a supernova. So mankind has known about supernova for many years.
Right.
However, the first time we detected neutrinos from supernova was in 1987, which is
Okay.
very recently when
Right.
we built neutrino detectors. Now, whenever we look at stars or even the sun, what we actually see is the light coming from it, and therefore we look at its surface.
Okay.
Light cannot tell us what happens inside the core of the star because the light cannot pass through the star.
Okay.
Neutrinos allow us to see what happens inside the core.
Okay.
Actually, what nuclear reactions happen inside the
Or
sun.
could be the core
or
of the
inside
stars, core of the sun?
Yeah,
And-
everything. So to understand inside of the sun, we actually need neutrinos.
Okay.
And similarly about supernova.
Okay.
Now, as I said, how a supernova explodes also tells us about how we came into being.
Okay.
So the new neutrino detectors that are being built are built such that they are efficient in detecting neutrinos that will come from a supernova.
Okay.
So when a supernova will explode, okay, about 10 to the power 58 neutrinos come out in 10 seconds.
Okay.
So
That's
whenever
that's a
something like
huge
this will
number.
happen in our galaxy,
Right.
we are now sure that we will see thousands or 10,000s of them in our detectors.
Right.
And from that we'll be able to actually know how stars explode, which is one of the big mysteries.
And for any
that
forward
we know.
movement now, as far as the supernovas is concerned, of course, you've got to wait for the next supernova to happen.
Yeah, of course, yeah.
Everyone is waiting.
Everybody
Right.
is waiting. Yeah.
Typically happens in about once in 30 years or so.
Once
So it's
in
about,
a
you know,
million.
overdue
It is
for
the
one.
neutrinos through which you will know that a supernova explosion has taken somewhere. So you can even alert the optical astronomer all around the world that a supernova explosion has happened there. Look at that direction, and after some time they will see it in light.
See,
In
neutrinos
fact, in
will come
1987,
about a day before the actual light comes, so
Yeah.
we know where to look.
I would come to you, Professor Datar. I mean, it's something of a huge interest. We've seen in our childhood serials like Star Trek. We used to see interstellar communication happening, and so I've read it somewhere that probably neutrinos could help us in building that kind of a communication. Is it true, or is it just purely a fiction?
Well, at this time, I think it is more in the realm of science fiction.
Okay.
But what you think is science fiction today can really happen.
But some kind of a research has already taken place as far as
Yes.
communicating
So
signals is
hundreds of
concerned.
kilometers is what has been achieved now. If
Okay.
you want interstellar, that's a much taller order, because you have to have much higher energy accelerators.
Okay.
You have to have PEV or something like that, which
Okay.
is orders of magnitude
However,
higher.
remember that hundreds of kilometers already is good, because if you want to send communication by light, it has to go via satellites. It has
Okay.
to actually go around the Earth.
Okay.
Neutrinos can go through the
That
Earth,
is the
so
point.
they
Yeah.
actually will reach faster
You cannot
than the
stop.
light
Okay.
can reach. So in fact, it's a faster than
So on
light
a lighter
communication
side,
or
the
something.
stock exchange broker in Tokyo will get information from New York a
the
little
Earth.
faster
Through the Earth.
than
And
via
that is not through the
neutrinos,
satellite,
and
but through the
can make his
neutrinos.
decision, which can help him make some more money.
Split-second,
You
you know,
would not-
the
you would not
news
need
coming
antennas
through the
and
satellite,
It
satellites.
right?
really sounds like a science fiction, but who knows, it might become a reality, because as they say, today's science could become the technology of tomorrow. Thanks to all my guests. It was a pleasure to have all of you on this program. Thanks.
Thank you so
Thank you.
much.